Previously, when we had been taking a look at how a tire rolls down a road, pointed out that in normal operation, when the tire isn't slipping, it has to be the case that the contact patch is stationary with respect to the road. Now, a car tire is definitely not a rigid object. The contact patch, the tire changes shape as it rolls. It's a little flattened out at the bottom. But a bicycle tire inflated to higher pressures is closer to being a rigid object. And we can extend this all the way to, say, a wagon wheel, which we can very closely model as a rigid object. And in all of these cases, we're going to come up with the same observation. This point right here has to not be moving, even though the center of mass is. Let's try to draw that a little more horizontal, shall we? There we go. All right, so what kind of constraints does that put on the rotational motion? Because remember, in the rigid body model, we can say we can completely describe a rigid object as a combination, its motion as a combination of the translation of its center of mass with the rotation about the center of mass. So if we think about just the translation by itself, so no rotation whatsoever, we could look at, say, these 3 points right here, and all those points would be moving at VCM. But the problem is I need this one to add up to 0. So what we're going to do is we're then going to add in the rotation. So this is rotation without translation. And what I realize is that for the rotation bit here, I need the tangential velocity here to equal the center of mass velocity. And while we're at it, that means that, say, here, the tangential velocity would equal the center of mass velocity. All right, so if I put the two of them together, so our rolling motion, what are we going to get? Well, here, when I add the two velocities together, I'm going to get, surprisingly, 2 VCM. At the center of mass, we're just going to be moving at VCM. And then we get the desired V equals 0 at the bottom. And you can actually see this. If you look at, say, high-speed, a photo of, say, a bike race or something like that, and look at how the tire is blurred, especially, say, if you're looking at, like, a still photo from a sprint finish at the end of a professional race, you'll see more blur on the bike wheel at the top than at the bottom. So this really does hold true. And we can also pick out that, say, these points here on the side, if we were to do them, I'll leave that as an exercise for you to convince yourself that this point here and this point here have a total velocity of square root of 2 VCM. But anyway, the constraint that we get if we're rolling without slipping, since the tangential velocity equals the center of mass velocity, we're requiring, or demanding, that's what the exclamation point means, that the center of mass velocity equal r omega. That's the only way that that can happen for us to have it so that the speed is 0 at the contact point, like we've seen before. Now, it is entirely possible to roll and slip, just to be very clear. So let me just do a quick example of that. I mean, the classic example would just be a car peeling out because you stomped on the accelerator too hard and there wasn't enough grip on the road. Kind of hard to do with more modern cars and computers that outsmart us. But an example that you might be more familiar with would be bowling. Unless you've got very non-standard form, when you let a bowling ball go down the lane, it's spinning backward-ish. You probably put a bit of side spin on it as well in order to get good pin action. But the center of mass velocity is still going down the lane. But in fact, in this case here, it's rolling backwards. And it'll keep that up for quite a while because bowling alleys have oil on them, and that's to enhance the slipperiness. And they do things where they change the kind of oil at different spots in the lane so that you can manipulate the coefficient of kinetic friction. Then at some point, as you continue to feel force of kinetic friction acting on the bowling ball, you get to a point where finally the speed hits 0, and then you actually transition immediately to the rolling without slipping scenario. And that's usually when you see the fairly pronounced hook of the ball. So in normal bowling, you aim a bit off center and design it so that it hooks in either between the 1 and 3 pins if you're a right-handed bowler, or the 1 and 2 pins if you're a left-handed bowler. Because if you go straight in on the head pin, usually what happens is you leave the 7 and 10 pins sitting all by themselves. And it's very hard to pick up that spare. Whereas if you hook the ball a bit and get it to pop into the pocket, as it's called, you can get good pin action that will hopefully take out all the pins. So I just wanted to be clear that this could happen where you end up having rolling with slipping. However, let's just go ahead and explore a little more what our rolling constraint can give us. So for instance here, let's think about a race. So I have a ramp here, and I'm actually going to have to try to draw this in 3D. Probably not going to go too well. Not too bad. Theta, let's say it's h high. And so we'll have a race where we imagine that we have a sphere, a cylinder, and a hoop. I tried my best with the hoop. Oh well. And although it doesn't matter, as we'll see, let's just say they all have mass m and radius r. So then the question is, who gets down there quickest? So go ahead and pause the video and give me your ranking of how you think the order of finish is going to go. All right, so let's go ahead and think about this. We can do this with energy conservation and our constraint. So if we start to make a table, final, initial, and we list all the forms of energy we can think of, we can think of translational kinetic energy, rotational kinetic energy, and gravitational potential energy. All right, so let's go ahead and fill in the values. We're letting all these go from rest, so we can make these 0. We can set y equals 0 to the bottom of the problem, making the initial gravitational potential energy mgh. And then we'll have 1/2 mv squared and 1/2 I omega squared. Now, it might seem at first blush like we would need to analyze this 3 separate times. But the first thing we can realize is that whoever's going the fastest at the bottom is going to win, because they'll have been going the fastest all the way along, since we can make h whatever we want. So by solving for, if we can just solve for the final velocity, we're good to go. The second thing is that in this case here, all of the moments of inertia have the same form. Remember, for a sphere, the moment of inertia is 2/5 mr squared. For a cylinder, it's 1/2 mr squared. And for a hoop, it's just, I'll say 1, for reasons that will become clear in a second, mr squared. So the point is they all have an mr squared, and then they have some number in front of them. So what we can do is we can just do this generically. We'll say that the moment of inertia of any of these objects is eta mr squared. Now, before you totally freak out about eta, you draw one like that. This is a Greek letter that physicists often use when they just want to make up a constant on the fly. In this case here, all I'm doing is saying eta will be either 1, 1/2, or 2/5, depending on whether I'm thinking about the hoop, the cylinder, or the sphere. So once I solve for the final speed, all I'm going to do is just think about what value of eta will give me the fastest speed at the bottom, and then that's going to solve my problem. So that's the idea there. All right, so let's go ahead and equate our energies here. So 1/2 mv squared plus 1/2. Now the moment of inertia, we said for all these things, is going to be eta mr squared omega squared, and that's equal mgh. So my first promise has been kept. I had promised that the mass didn't matter, and it doesn't. All right, now because we are rolling without slipping, we require that our center of mass velocity equal r omega. So that's going to give me v squared equals r squared omega squared. Hey, I just happen to have one of those right there. So that's v squared. So now I can write this as 1/2 v squared plus 1/2 eta v squared equals gh. All right, so we can group out just a little bit. 1/2 times 1 plus eta v squared equals gh. And finally, we get that v is equal to the square root of 2gh over 1 plus eta. All right, so then we can figure this out. Whatever gives me the smallest denominator will give me the biggest final speed. So that if I go and take a look at my list here, 2/5 is smaller than 1/2 is smaller than 1. So this means my winner is the one where eta equals 2/5, and that's our sphere. And our loser is the one where eta is equal to 1, which is the hoop. And you'll notice here too that once we made this identification, the r went away. So that was my second promise kept. So the main thing that matters is just the shape of the object. Let it roll without slipping. The one that has the mass most concentrated towards its rotational axis is the one that wins. All right, so in the next set of videos here, we are going to start taking a look at figuring out how to do vector definitions of our angular variables to handle more complicated situations. Catch you over in the next video.